welcome to the deep dive. You've handed us a really fascinating stack of sources today. It's a chronological review spanning from 2019 to 2025 that charts this incredibly rapid evolution of AI in consumer finance. Now, these sources, they're dense, they're technical, but our mission for you is simple. We want you to quickly get the key technological breakthroughs and, I guess, the strategic challenges that came with applying these advanced AI models like neural networks to the really complex, highly regulated world of consumer credit.
Exactly. Our deep dive today is, a kind of high-speed masterclass. We're cutting right to the core of this transformation. We're tracing the path from just, using new powerful algorithms to fundamentally reshaping the underlying math and the very infrastructure that modern lending is built on.
So this isn't just a story about finding a slightly better prediction model.
Oh, not at all. The innovations we're going to talk about weren't driven by some technical curiosity. They were forced. They were forced by regulatory demands, compliance, and by the need to optimize for true financial objectives like profit and loss. It's the story of AI shifting from being a modeling problem to really a foundational engineering problem.
Okay, so let's unpack this timeline. We'll start around 2020. The first big leap, as you said, was the move to neural networks. They offered huge predictive power, but what was the immediate trade-off? What did the industry have to solve to make them work?
The trade-off was scale. Specifically data volume.
Data.
Yes. Neural networks as a class of algorithms they're notoriously data hungry. To really get that predictive edge over the older models, the amount of training data you needed had to increase, exponentially.
And I'm guessing without that huge increase, the sources suggest these powerful models can be worse than useless.
That's the crucial warning. The sources are explicit on this. Without these massive, carefully managed data sets, we are talking exponentially more data, the models don't just underperform. They can actually be, and this is a quote, quite harmful.
Quite harmful. Why is that?
Because they can overfit, or they capture these strange correlations in small data that just don't hold up in the real world. So solving that data scale problem was the absolute non-negotiable first step.
Okay, that brings us into 2021. And this is where it gets interesting, because the pressure of regulation really started to shape the timeline. Instead of just chasing prediction accuracy, the industry poured resources into, of all things, compliance.
Why apply this cutting-edge AI to what most people would see as, a boring administrative task?
Because consumer credit is one of the most heavily regulated industries out there.
Yeah.
You've got fair lending rules, mandated explainability, the safety and soundness of the whole financial system.
Right.
For decades, the industry lived in what the sources call the safe confines of traditional, very transparent, very vetted scoring models.
And those old models, because they were simpler, they were much easier to explain to a regulator, right? Precisely. The moment you bring in a sophisticated kind of black box model like a neural network, all your old simple methods for checking for fairness or providing explanations, they just become obsolete instantly.
So stepping outside that traditional zone meant you were inviting massive regulatory scrutiny.
Exactly. The industry had to prove that these new models weren't inherently biased or just totally uncontrollable black boxes.
So if they couldn't go back to simpler models without losing all that predictive power, they had to tackle the complexity head on. It was the only way forward to, I guess, use AI to police AI.
That was the only viable path. You had to match the sophistication of your underwriting model with an equally sophisticated compliance system. This meant developing entirely new machine learning-based methods that were focused specifically on model explainability and fair lending testing.
The sources mentioned a couple of systems here, things like LDS and SHAP. Can you break those down for us? What do they actually do?
So at a high level, they provide really granular, feature-by-feature model explanations. Take SHAP, for example. That stands for Shapley Additive Explanations. It's a technique that helps you dissect exactly which inputs and by how much led to a specific decision, like a loan denial. And LDAS, or local dependency analysis systems, those often help test for bias at very specific points in the data. You can make sure that a certain group isn't being denied for prohibited reasons, but for legitimate risk factors.
So you need that kind of detail, because if your model's working in, say, 100 dimensions, you can't check its fairness with a simple Excel spreadsheet.
That's the challenge in a nutshell. It was a huge step toward regulatory maturity. The models weren't just powerful anymore, they were auditable and, transparent to regulators.
That foundational work set the stage for 2022. The focus shifted from compliance to the core financial math, the creation of what the sources call a proprietary loss function. Now, for anyone listening who isn't in machine learning, the loss function is basically the model's goal. It's the error it's trying to get as low as possible.
That's right. And traditionally, the industry used a very elegant standard called log loss. It's fast, it's efficient, and it's great for simple binary outcomes. Did the loan default or did it not? A 0 or 1?
But I'm guessing that simplicity becomes a huge financial problem when you're talking about a multi-year loan.
Right.
What are the weaknesses there?
There are three really critical failings. First, and this is the most damaging to the bottom line, log loss treats a loan that defaults in the first month the same as a loan that defaults in month 59.
Ah.
Both are just a 1, a bad outcome. But financially, the cost to the lender is completely different. Second, it handles prepayments really badly. Someone paying off their loan early is a good thing, but log loss often ignores it or even treats it like a bad outcome.
So the model is trying to be mathematically pure, but it ends up being financially irrational.
Exactly. And the third point is that it fails to capture the magnitude of time-based error. If the model predicts a default in month 3, but it happens in month 2, that's a small error. But if it predicts month 3 and it really happens in month 53, that 50-month gap isn't properly penalized.
So the model might be minimizing a generic error, but it's totally failing to minimize the actual financial error.
And that is the key innovation of 2022. The real financial goal is to minimize the difference between expected and actual cash flows, measured in net present value, or NPV.
And to do that, the model has to make these incredibly complex predictions. I think one source said for a 60-month loan, it's making 120 predictions at the same time.
That's correct. For every single month, you need a probability of default and you need a probability of prepayment, so 60 of each. That creates this huge 120-dimensional optimization space.
This is where that visualization analogy from the sources really helps. If you picture that space as a heat map, you're trying to find the single reddest location, the point of minimum financial error.
Right. And if you use the generic log loss function, the model's optimization path, it gets close, but it subtly misses the mark. It misses that true reddest spot because the simple function just steers it wrong in that complex space.
But the proprietary loss function, this custom-built thing, it forces the model to follow the exact path that leads directly to that minimum financial error.
Yes, and that difference in the path makes a very significant difference in the final error and the quality of the predictions. This was the moment AI stopped being just generally accurate and started working for the lender's actual bottom line.
Okay, moving into 2023, the focus shifts again, this time from the internal math to the external world, the problem of macroeconomic instability.
Yeah, most machine learning doesn't have this problem. Like the source material says, dogs always look like dogs no matter what year the photo was taken.
Right.
But lending is fundamentally different. The way people repay loans, the overall level of defaults, it changes dramatically over time because of recessions, job markets, inflation, the macro economy.
So standard models were just treating time as if it didn't matter, assuming past behavior was always relevant.
Which is really dangerous in finance. The solution was to build systems that could adapt dynamically to these changing macro conditions. This allows the model to sort of natively pick up on statistically significant trends the very moment they appear in the data.
What kind of trends are we talking about here? What would this system catch without a human having to step in?
It's looking for two types of shifts. First, big aggregate shifts. Like, if suddenly the default rate across the entire country is twice as high as the historical average, the model sees that.
Okay.
But also much more granular segment-level shifts. Say, a specific group that was always low risk, maybe, government employees or people with a certain degree, suddenly starts struggling.
The model picks up that unique shift just for that subgroup and adjusts their risk profile on the fly without anyone having to manually retrain the whole thing.
That's the power of it. It keeps the underwriting relevant even when the economy gets choppy.
All right, we are racing toward the present. 2024 tackled what the sources call the forever problem in lending, adverse selection. Explain that for us. Why is it such a difficult problem?
Adverse selection is, well, it's this immutable truth in lending. The people who are actively trying to get your money are, statistically speaking, worse risks than people who aren't asking for a loan.
Right.
The models needed a way to spot the suspicious borrower, the one who looks great on paper but seems a little too eager.
You mean the person with a clean credit score who is, and I'm quoting, super happy to take a high annual percentage rate loan. That happiness suggests they know something you don't.
Exactly. And the technical solution they came up with was incredible. They decided to treat the assigned APR, the model's own output, as a new input feature for the model.
That's a clever way to use the borrower's behavior as data. But technically, feeding the output back in as an input, that creates an infinite loop, right?
It does. The risk depends on the rate, but now the rate depends on the risk. You can't let that loop run forever. It has to converge. And fast, we're talking milliseconds, while the borrower is sitting there waiting for a decision online.
So the fix for adverse selection created this impossible demand on the computing infrastructure. Running many parallel instances of the model just to force a quick answer must have been a huge drain on memory and compute power.
It was immense, and that pressure led directly to the next big innovation: the creation of the block-sparse matrix format. This is the ultimate example of AI maturity becoming an infrastructure problem.
So what was the specific data issue that made them rewrite something so fundamental?
It was all about redundancy. Remember that 60-month prediction framework? To train the model, you need 60 rows of data for a single borrower. So if a borrower had a credit score of, say, 714, that one number 714 was duplicated in all 60 of those rows.
The system was wasting massive amounts of memory just storing the same number over and over.
Precisely. And at the scale and speed they needed for that infinite loop problem, this memory waste became a paralyzing bottleneck. So the block-sparse matrix format was designed to compress it all. It only stores the unique data once, and then represents all the repeated data with zeros.
And the result of that fundamental change.
The sources say it led to an immediate memory reduction by a factor of 20, and that will grow to a factor of 60 over time as the loans mature. It just shows the level of custom, low-level engineering you need to make these models work in the real world.
That remarkable feat brings us to today, 2025. After tackling the algorithms, compliance, macroeconomics, the math, and the infrastructure, where's the R&D focus now?
The current frontier, from what we can see in the latest materials, is all about embeddings.
Now that's a concept we hear about in language models and image recognition. How does it apply to lending?
Embeddings are techniques for taking complex, often unstructured data, things like text or subtle behavioral patterns, and turning them into dense numerical vectors that a machine learning model can understand.
I see.
What this really does is it opens the door to using many more kinds of data than traditional credit modeling ever could.
That really synthesizes the whole journey perfectly. We went from 2020, just using a powerful algorithm like a neural network, all the way to 2024, where the entire computing infrastructure had to be rewritten from the ground up to handle these proprietary features.
The core takeaway for you is this: advanced AI in lending isn't about the algorithm you pick anymore. Its success is now defined by the proprietary goal you design for it, the compliance systems you build around it, and the custom, highly optimized infrastructure you create to make it all run. That continuous, specialized effort is just non-negotiable.
And that leads us to our final provocative thought for you, the listener, to explore. Given this 2025 focus on embeddings and unstructured data, think about this. What specific new sources of information, things beyond credit scores and income, might these models be using right now to evaluate risk? And how could that fundamentally change our very definition of what creditworthiness is?
A fascinating thread to pull on.
Thank you for sharing your sources with us for this deep dive. We'll catch you next time.